And we're going to calculate the continued fraction for the Ramanujan, Rogers-Ramanujan's continued fraction, and for the value of e to the minus 2 pi. And we will get this result, hopefully. Now, if we start, we can use an identity that is quite well known. If you have alpha times beta equals pi squared, you will get the following identity, which is that continued fraction to the e to the minus alpha times 2 plus the golden ratio times continued fraction to the e minus beta times 2 plus the golden ratio equals it's square root of 5 times the golden ratio. Okay, and if we multiply this out, we should get that the continued fraction squared plus, if we replace alpha and beta by pi, we get that the wanted continued fraction plus 2 golden ratio times the continued fraction plus the golden ratio squared equals square root of 5 over the golden ratio. And we can use the quadratic equation to solve this. I will not provide the equation because it's rather simple. And you'll just get minus 2 times the golden ratio plus or minus square root of, you'll bring out a fourth, you'll get a 2 in the front, and you'll just get golden ratio squared minus golden ratio squared minus square root of 5 golden ratio, and these cancel out, and the 2's cancel out in the bottom, and you'll just get the result. So the result is plus or minus square root of 5 times the golden ratio minus the golden ratio. And we got this result from this equation. Now, you can replace alpha and beta with, for example, pi over 2 times 2 pi, which would place minus 4 pi here and minus pi here. But this is the simplest form to achieving a value for the equation. Now you can use this equation as well, which is 1 over the continued fraction to the fifth minus the continued fraction to the fifth of q equals the eta function over the eta function to the power of 5, and this to the 6 and plus 11. Now remember, q here is e to the 2 pi I tau. So you could use this, but this is quite arduous because you have to find values for the eta function. If you find, you could use many different techniques for acquiring these values, but they're a bit arduous to achieve. There's this formula, it's called the Chola-Selberg's formula. It's quite interesting. It's a way to acquire values, but it's to a certain number field. But it's a really interesting formula, and this one is derived by Ramanujan, and there are alternatives for example, the modular lambda function, um, but it's a bit different. For example, there's tau fourth here instead of tau, for example. But I think that's um, I think that's I am well pleased to start with this example, and hopefully later I can provide other examples. But now we know that the value of this is this, and we have achieved the result.